Well, good afternoon, and thank you very much for coming today. I'm glad to have the opportunity to address you, and I hope that what I'll have to tell you will be at least somewhat interesting and hopefully informative. I hope the title that I've given this talk isn't too flip. The title is How Dense Can You Get? And that's not meant to be flip. It's actually meant to be a valid question. What happens if you squeeze stuff down? How dense will it get? And what can you say about the hypothetical properties of matter as you get to very high densities? What can we say about those things based on what we know, the currently evolving state of knowledge about nuclear interactions at very, very short ranges, strong interactions at the level of nuclei and subnuclei, the constituents of nuclei. So those are sort of the kind of things I want to talk about today. And the point that I'll be making is as you get more dense, the constituents that make up matter get closer, and as they get closer, obviously the interactions that are strong at short range become more important. So the two things go hand in hand. As you get more dense, short range interactions become more important. And that's really sort of the theme of this talk. So let me start with some data. These are data that I acquired a few years ago, and I'll tell you something about this in a second. Actually, I'll tell you about it now. I think it's somewhat relevant. It's tangentially relevant, but it's relevant because I think it illustrates in one photograph, and I can't see it very well because the lights are in my eyes, but hopefully you can. It illustrates in one photograph the whole sort of gamut of densities that we sort of observe in nature. Okay, pretty much everything is represented somewhere in this picture, even if you can't see it. This was taken in the pre-dawn hours in the spring, and I'll tell you in a little bit what year. I'll let you try and guess what year, but I'll tell you in a little bit. Does anyone know which direction I'm looking in? Can anyone guess? By looking at the stars here? Maybe not. This is towards the south or the southeast, more or less south-southeast. I'll talk more about that in a second. And there's a number of interesting features. This is in the mid-spring, and it's just before dawn. Okay, and I took this picture, let's see. So there's a number of features, and I hope you can see them. One feature that probably stands out, I don't know, many features maybe stand out, but one feature that might stand out as you look at this picture is you'll see this diagonal streak across the sky. Does everyone see that? Mm-hmm. Right? That obviously is the Milky Way. Okay, that is our home galaxy. And the reason it looks the way it does is because the Milky Way is a flat disk. We live in a spiral galaxy, and we're looking at it edge on. So given that we live on an outer arm, on the periphery of the Milky Way, when we look at the Milky Way, we see the entire thing as a flat disk seen edge on from the side. Okay, so we live in the exurbs. If there were a galactic election, we'd be the exurbians that everyone's trying to get votes from. We're way out. Okay, we're in Stafford County or something. Okay. Okay. So as you look towards the center of the galaxy, things get very, very dense. Okay. You can see the dust clouds probably. And is there a pointer I can use? Actually, I don't have a pointer. Is there a pointer available? It would be useful if I could get one. Do we know if there's such a thing? I should have asked about this before. Either a laser or something, so I can point out features. Thank you very much. Okay. Well, so, sorry I didn't ask about that earlier. It should have occurred to me. So, towards the center of this band of light, you can see a lot of dust clouds because you're looking towards the center of the galaxy, right? Things get very, very dense. There's a lot of stuff going on there. And in fact, you can't see it by definition, but there's very good evidence, not absolutely conclusive, but pretty good evidence that there might be something at the center of the galaxy that is very, very massive and very, very dense. Okay, infinitely dense, perhaps, if such a thing is possible, and if in the real world. But astronomers do believe right now that at the very center of the galaxy, looking right at the center of this, right up here in the middle where all the dust clouds are, there is a supermassive black hole, supposedly. And that supermassive black hole, people have calculated based on the proper motions of stars that they can measure, that it probably has a mass of something on the order of 40 million suns. So it's a pretty heavy object. And it's supposedly, according to the theory as we understand it, and of course there are great limitations to the theory of gravity right now, as you probably know, this is 40 million suns with no volume, right, at a singularity. Singularities typically aren't real. So there's probably physics going on that we don't understand, but we have a very, very massive object located at a single point, supposedly. Well, there's a lot more to be said about that, but that's a whole other lecture. In fact, that's a whole other class, right? Okay. So a black hole is something that is in principle infinitely dense, or at least very, very, very dense, and that's pretty much as dense as you can get, by definition. You can't get any more Catholic than the Pope, and you can't get more dense than a black hole, right? Supposedly. All right. Now, as you move away from the plane of the galaxy, okay, as you move up or down away from the plane of the galaxy, you're looking out into interstellar space, or intergalactic space, in fact, right? So as you move away, things get less dense. And if you're far enough away from that plane, so the bulge of the galaxy, if you could see it on this picture, and this is not a great picture, this is a very amateur picture, but if there's a bulge at the center here of the galaxy, as you move away, you move into interstellar space and into intergalactic space, which is, you know, very, very diffuse. There's very little. There's these huge voids of empty, almost empty space between stars and between galaxies, essentially. And in those places, there's almost nothing. There's something, but there's almost nothing. So the interstellar medium is about the least dense thing you can get. And everything else in this picture is somewhere between those two extremes. Between the interstellar medium, which is very, very diffuse. You know, you have maybe one, you know, perhaps, you know, the equivalent of one hydrogen atom in, you know, cubic kilometers or something, versus having 40 million suns at a single point at the center of the galaxy, if that is actually true. And, you know, it's still up for debate, but there's good evidence for it. So everything else here falls in that range. Now, what else is going on here that's interesting? If you're familiar with the sky, and some people are and some people aren't, you might notice some asterisms. You might notice some patterns here. And this is where it'd be useful to have a pointer. But thank you. That would be a good place to start. Thank you, as long as you don't hit me with it. If you don't like what I say, thank you. Thank you very much. Okay. So, right, this is the galaxy here. This is the plane of the galaxy. This is about where the bulge is, okay, the center of the galaxy, where we, thank you very, very much. Thank you so much. And thank you. Okay. Okay, well, better than none. Okay, there, this way. All right, so, yeah, this is about where the bulge is, right? And this asterism here, you might recognize, this is called the teapot. It's the teapot of Sagittarius, okay? In the southern sky, this is, you can see, this is sort of the handle of the teapot, this is the dome, and this is like the spout of the teapot, and it points right towards the center of the galaxy, right? And, you know, it points to a lot of interesting objects because you're looking towards a galaxy. You have lots of things like this. This thing here you might notice is sort of a fuzzy object. This is an open star cluster, okay? This thing is known as well, its original name is the Ptolemy cluster because it was recorded and observed by the astronomer Ptolemy in the 1st century AD in Egypt, and the name stuck. So these things don't change very much over historical time, right? But in fact, this is a very dynamic place. What's going on here is this is actually a place where stars are being born. Okay, there's stars being born, and they're sort of surrounded in their gas from which they're emerging, and they're moving apart. This is a star cluster, the Ptolemy star cluster. You have another star cluster here. You have one here. Lots of this stuff along in the Milky Way. You have some other ones back here. You have lots of these star clusters, which are sort of an intermediate density, right? You have lots of gas, and then you have these congealing stars that are forming and moving outwards into, you know, and spreading out. Okay, that's sort of intermediate. And if I show you a picture of sort of a star map of this region, okay, this is a sort of a star map of this region. You see here the teapot I was talking about, right? The brighter stars are obviously bigger circles. And, you know, this is the handle I was talking about, and the spout and such. Here is the Ptolemy cluster, right? The open star cluster. Here's another open. Here are some more open star clusters. Other various objects. These are named M. They has M numbers. This is their catalog name. They were cataloged by a fellow by the name of Charles Messier back in the middle of or late part of the 18th century because he was a comet hunter, and he wanted to see. He wanted to know where all the fuzzy stuff was, so when he found something new that was fuzzy, he'd know it and he'd be the first person to see the comet and get the comet named after. Okay? So these M numbers, you know, this was the 7th thing that he cataloged, was M7, was Ptolemy's cluster. Okay? Now, the interesting thing is, if you compare this picture to the picture, or this chart to the picture I showed you, there's a few things on this chart that or there's a few things on the picture that aren't on the chart. You may have noticed them. The one obvious thing is, if this point here, this star here, if I'm looking at it right, this star here is this star Lambda Sagittaria here. This star here is up here, right? And then this star over here is this. So there's this really bright object here that appears nowhere on this chart. Any ideas what that might be? Something really, really bright that's not on a star chart, but it is here anyway. It could be a UFO, but you know. That would be really cool if I'd caught a supernova. I wish. No, I wish. That would be, if I'd taken a picture of a supernova, you know, that'd be cool. No.
How about an airplane?
It could be an airplane, but okay, here's another point. So this is a timed exposure. So this is about a minute-long exposure. So you can actually see that some of the stars are sort of, they're not really points. They're kind of, they're moving a little bit. So if it were an airplane, you wouldn't see this, you'd see a streak, but that's a good guess. It's a planet. That's exactly what it is. This is, in fact, this is Jupiter. Jupiter just happened to be in the house of Sagittarius at this particular point in time, so it was the dawning of the age of Sagittarius or something, I don't know. But, okay, so, and you know, Jupiter is something, you know, it has a density of what? It has a density of somewhat lower than the Earth because it's a gas giant. Okay, so it's, you know, has a density somewhat more than approximately water density. And then, but at the very core of Jupiter, you have a very dense core, which is supposedly, at least according to current theory, is solid carbon, or something like that, maybe even a diamond, I don't know, but it's pretty dense, okay? So there's a range of densities there. And the really interesting thing here, has anyone noticed anything interesting else on this picture? Hint, Messier was looking for them. So, in the middle here, this thing? Well, this is a star. This is the star. This thing, there's a comet here. There's a comet here. Yeah. This is a comet that I happened to catch. I was looking for it when I took this picture. This comet, you know that I'm looking south-southeast because it's pointing away from the sun, so the sun is going to be down here just before dawn. And the tail of the comet always points away from the sun because you have, you know, the radiation pressure, the radiation, and the particles that are streaming away from the sun called the solar wind, which pushes away the dust and the ions away from the head of the comet, away from the sun. Now, the comet is actually moving in this direction. So it's moving in the direction of the tail, but that doesn't matter, okay? The tail is leading the head in this particular case. If I tell you when I took this picture, you'll know what that comet is. Do you want me to tell you the comet, or you want me to tell you the date and have you guess the comet? Huh? The date. I took this picture when I was just after I left MC. It was just a couple of months after I left MC in 1986. It's Halley's comet. Yeah, it's Halley's comet. Not that one. That's a different one. But if you have a dance party, you know, go for it. Okay, this one, this Halley. Actually, I think he pronounced his name Halley, is what I'm told. That's what I'm told. I don't know. This was in the 18th century. They did things funny back then. British always do, huh? Like the curve, right? Exactly. So apparently he pronounced it Halley, and he lived between 1656 and 72. And he basically confirmed Sir Isaac Newton's University of Theory of Gravitation by predicting the return of his eponymous comet, named after him. I don't know if it's posthumous or if he was still alive when they did that. I'm not sure. Maybe someone knows. Was it posthumous? In 1758, he said it's going to come back, and he was right. And he basically calculated exactly where it was going to be based on using the theory developed by Sir Isaac Newton. So it was this guy basically confirmed the Newtonian universe that was just emerging, and people were starting to think, well, the universe is a big clockwork place. You can describe everything that happens and understand exactly what's going to happen. That changed later on, but at that point, people were like, right there. It's like, okay, we can get everything. We understand things. Okay, so this is the Halley I'm talking about. So just a couple. Let's see. Do I want to go on? Okay. Halley's comet is a comet that returns every 76 years or so. Okay. You may have seen this picture before. This is a picture of the Bayeux Tapestry, which commemorates the last time that the Brits were conquered by the French, in fact, or the Normans. I guess they're French. The Normans, okay, in 1066, where Harold the Saxon was defeated by William the Conqueror. And in fact, if you look in this tapestry, there is a picture, or is a drawing up top of Halley's comet, a foreboding of doom for Harold, but not for William, obviously. And that was in 1066. And it's believed that was Halley's comet. In fact, Halley's comet, there's records of it going back more than 2,000 years. They didn't know at the time it was the same comet, but if you look back and then you calculate the trajectory according to the laws developed by Newton, okay, you say, oh, well, there it was. That was the one. That was the one they were talking about all those times. apparently Halley's Comet was in the sky when Genghis Khan was making his way towards Europe. That was good for the Mongols. It wasn't so good for maybe perhaps the folks living in the Middle East at the time. But that was another thing. And of course, this brilliant man will forever be mentioned every time Halley's Comet is mentioned because he's Mark Twain. And he just had a knack for so many things. He's one of my heroes, actually. But he was born when Halley's Comet was in the sky in 1835. And he predicted he would die when Halley's Comet was in the sky in 1910. And in fact, his prediction came true. So anytime you mention Halley's Comet, you got to mention Mark Twain or Samuel Clemens. And he did. And 1910 was apparently an amazing sight. When the comet came through, the Earth actually passed through the tail of the comet. And it was the comet apparently went across the sky. It was a beautiful view. People were scared. People were buying comet pills. There were all kinds of charlatans selling comet pills. People were buying gas masks because they knew they were going to pass through the tail of the comet, not realizing how diffuse the tail is, right? And all these terrible gases, they were going to get suffocated. People were buying gas masks. There were millennial cults that actually went up to mountains and waited and thought they were going to be taken up to heaven, and there was going to be the rapture was going to happen at this point. It was a crazy time. Everyone saw it. Also, there weren't that many city lights, so everybody saw the comet. In 1986, when I was 18 years old, you couldn't see it. It was really awful. It was the worst appearance of Halley's Comet in 2,000 years. It was the worst in 2,000 years, and I had the good luck of being around the worst appearance of Halley's Comet in 2,000 years. And I've been waiting for this since I was a kid. I was really disappointed. Well, I was not disappointed, but because I saw it and I was happy about that. But I was not what I had expected. I've seen much more impressive light shows than Halley's Comet. But 2061 is supposed to be pretty good. So if you're around, mark your calendars. And 2137 is supposed to even be better. So if you're around for that one, that should be really cool. So keep that one in mind. Now, what was I going to say? Right, in 1986, what basically happened was when the comet was at its brightest point, it was behind the sun from us, so we couldn't see it. When it had its longest tail and it was brightest, we just couldn't see it. The other thing was, for those of us who live up in the northern hemisphere, okay, when it was coming towards the sun, before it developed its tail, it was visible in the northern sky. So if you're in Maryland, like I was, that picture was not taken in Maryland that I showed you. If you're in Maryland, you really never got to see the tail. Now, what I did do, I remember, I'm pretty sure this was a Wednesday, because in November of 1985, when I was a student here, and I was taking ES 240 at that time, I remember, on Wednesdays with Dawn Day, okay? I remember getting in my car and driving up 28 out into the boonies, the boonies which are now totally built up, to get away from the lights, and look up and took out my binoculars, and sure enough, there was a fuzzy spot there that was the first time I'd seen Halley Comet. This was in November of 1985, but no tail. So after I left MC, in April of 1986, when it came back from behind the sun and it was visible farther south, I had to go see the thing. So I actually went down to Texas and stayed with a cousin down there and went out in the brush in San Antonio before dawn and took the picture that I showed you there. I took that picture with a tripod, a 35mm camera, some Tri-X film, Kodak Tri-X film. I don't know if you can buy that stuff anymore. Open the camera for a minute. Actually, I did it for 30 seconds, a minute, 2 minutes, 10 minutes, a whole bunch of exposures, took it back, developed it, see which one came out best. In fact, I learned how to develop Tri-X film in Science East, when we used to have a darkroom, which now is a closet for paper and pens. But that's where I learned to develop Tri-X film. Okay, so there's an MC connection. All right, so having talked about that range of densities and all the different things that have different densities, so here's sort of a synopsis of sort of the densities of various things that we know about. So if you take water as sort of your standard, right? Water has, in terms of density, in terms of grams per cc, water has a density of 1 gram per cc, pretty much. So relative to water, you have things that are very, very diffuse, right? So I talked about the interstellar medium has a density that's about 10 to the 25th times, 10 to the 24th times, one with 24 zeros, not 25 zeros, less dense than water. And at the other end of the scale, well, I have nuclear saturation. Nuclear saturation is basically the density at the center of a big nucleus like uranium, which is about 10 to the 14th times more dense than water. And in fact, I'll talk a little bit about neutron stars. Neutron stars can be perhaps as much as 10 times more dense than a nucleus. So a neutron star would be just about there at about 10 to the 15, perhaps, on average density, grams per cc. Not that, astronomers ever use grams per cc as units, but, just to make it understandable. In fact, I used to work at the Naval Research Lab down in Washington, and I worked around a group of radio astronomers. And you know how when people have like a baby or something, they'll put up a picture of a baby on their door, right? And they'll put how long the baby is and how heavy the baby is and all the details of the baby. Well, radio astronomers being who they are, he put up a picture of his baby and he put the baby's dimensions in kiloparsecs and in solar masses, and yeah, it was. So units are important. You all know that units are important, but what units you use, that's sort of arbitrary, right? It's just what you put in your exponent, right? So if you want to measure your baby in kiloparsecs, be my guest. I don't know if the baby will like it, but anyway. So this is sort of the range. And so the solar corona, okay, which is the outer atmosphere of the sun, okay, is about 10 to the 20th times denser than water. And then you have some stuff that we sort of deal with on a daily basis, air at sea level, liquid helium. Well, you don't see that regularly, but liquid helium's there. And then you have this range here, which are the sort of things we deal with regularly. These are atomic things, right? So you have water down here, and then you have sort of atomic, these elements. You have aluminum, which is not very dense, and iron and zinc and copper and lead that I typically would think of as being a very dense thing, but actually it's not really the densest metal around. I mean, I'm sure the chemists know that, but I didn't really know that until I decided to make up this picture to sort of illustrate. And I was like, oh, lead is only about 10 times more dense than water. Gold is a lot more dense. Gold is the densest thing that we probably deal with on a regular basis, about 20 times more dense than water. And of course, if you deal with plutonium, I hope you don't have to, but if you do, plutonium is pretty dense, atomic plutonium. In a clock, I suppose you could in a clock, that's right. That's pretty dense stuff. So that's about as dense as stuff gets, is sort of in the normal realm, I guess, right?
Where's uranium?
Uranium would be somewhere, I'm guessing uranium is actually somewhat less dense than plutonium. Somewhat less dense than plutonium.
But talk about depleted
right.
uranium around.
Right. Now, I'm talking here now, these densities are not the densities of the nuclei. These are the densities of the atoms.
Yeah.
So, right. So the nuclear, or the density of the nucleus of uranium would be up here. Okay. And then you have things like the solar core, which is pretty dense. You have white dwarfs. I'll talk about what those are. Those are stars that are in at the end stage of their lives, but they have a very long retirement. They retired when things were still good, so they have long retirements. And then your neutron stars would be out here, as I said. And then if you talk about black holes, well, black holes, I don't know what black holes are really. I don't understand that physics very well. I don't think anyone really does. But a black hole, if it's infinitely dense, then I can't put it on the scale even if it's logarithmic, because the log of infinity is still infinity. So it won't fit on this PowerPoint. I tried, but I couldn't do it. I'm sorry. Okay? All right. So that's sort of a synopsis of sort of everything that we saw in that first picture. All right, so here's some questions that I just sort of want to explore with you and talk about in the time we have. First of all, well, how can you compress matter to very high densities? There's a number of ways. There are different ways you can compress matter. One way to do it is to sit on it, right? You sit on it, you squeeze it down, So, you use gravity, right? And if you're talking about very massive objects, gravity is a good way to squeeze things down, all right? What prevents a massive object from gravitational collapse? Why doesn't gravity just continue to collapse things until they become singularities? Well, basically there's got to be repulsive forces between the constituents of the stuff that somehow balance the gravitational force. Stands to reason, right? So getting this leitmotif of the forces, the short-range forces, very dense things. Okay, so we're talking about the repulsive forces. How dense can matter get before it actually becomes a singularity of infinite density, i.e. a black hole, if such a thing exists? Well, that depends on the details of the nature of the repulsive force between those constituents, which is something that is, a topic of active study at many places. And finally, probably most interesting, is what kind of new properties of matter do you encounter as matter becomes very dense? What new things do you notice that you hadn't noticed before? What new phases appear? Well, basically, as work is done on matter to compress it, You put energy into the system, and new degrees of freedom open up. This answers sort of the question we had at the beginning, right? You have new degrees of freedom that become important and take up energy, and you get new behavior that you didn't see, that wasn't important at lower energy regimes. But as you go to higher energy regimes or higher densities, those degrees of freedom or modes that can take up energy become more important. And you can get new phases, and they depend, once again, on the details of the interactions between the constituents of matter. Okay, so this is sort of where we're kind of going. Okay? All right, so talking about stars, and there's other ways to get dense matter, but let's talk about stars because that's their fun. Okay, stars are objects that are in hydrostatic equilibrium. They're balanced for the most part, unless they undergo some kind of violent change. For the most part, most of their lives, they're generally in equilibrium. So you have different types of stars that use different mechanisms to provide a balancing pressure to keep them from collapsing under the force of gravity, right? Different mechanisms. If you have your typical hydrogen-burning stars, like our sun, okay, they're called main sequence stars. They basically, it's radiation that's generated in the core that pushes out and prevents the gravitational collapse. If you have things called white dwarfs, I don't know if it's dwarfs or dwarfs. I always see it written dwarfs, but it sounds funny to say dwarfs. But I always see it written dwarfs, so I don't know. Anyway, that's held up by something called electron degeneracy, which I'll talk a little bit about. Neutron stars are held up by hadron degeneracy, and I'll tell you what hadrons are. Hadrons are basically things like neutrons and protons are examples of hadrons, the most typical examples that we deal with on a daily basis, or to the extent that they exist, right? Then you have possibly other exotic objects, things like quark stars, strange stars. Do they exist? Do they not exist? There's astronomers out there on Chandra who say, yeah, we saw something that looks like it could be a quark star, yeah, but who knows? And people don't believe them, and they have big fights, and they beat each other up, and no one really knows. But this is pretty darn speculative, okay? There's good candidates that, for white dwarfs and neutron stars that, do everything you'd expect a neutron star or a white dwarf to do. Neutron stars, you have plenty of, like things like pulsars that, clearly are something very similar to a neutron star. Now, you don't know for sure, but the theory works. In fact, speaking of this matter, has anyone ever seen a picture of the Crab Nebula? The Crab Nebula, right? It's very, you see these beautiful pictures in color and stuff, in false color, but that was actually a supernova that happened in, in the 12th century, 13th century? No, it was sometime in the Middle Ages, and no one in Europe saw the supernova. Nobody saw it. I mean, if they saw it, they didn't care. But in China, they recorded it, and they made a note of it. And where that supernova happened, there was this big ball of gas. And it turns out that right at the center of that ball of gas, there is a pulsar, which, probably the remnants of that star that exploded, left behind a dense core. That's a very good candidate for a neutron star. So there are, this is not so speculative. We believe this stuff. This stuff, who knows? And then, of course, black holes, are they really singularities? What does it mean to have equilibrium for a singularity? I have no idea what that means. There's physics there I don't understand, and I don't think anyone really does, but they understand it better than I do, but it's speculative. Okay. So let me talk about each one of these things. Hydrogen-burning stars. I talked about hydrogen-burning stars being main sequence stars. What does that mean? Well, most stars, normal stars, spend the vast majority of their lifetime in what's called the main sequence. Okay? If you plot along this axis, the vertical axis, the brightness, the absolute brightness of a star, so that's the brightness of the star at a standard distance away from the star, okay? So we have to know how far the stars are, and that's a whole other lecture, right? If you plot the brightness of the star versus its color, which is a proxy for its temperature, you find that most stars fall along this curve. Most normal stars fall along this curve. What does it mean to be normal? You're like everyone else. So the really bright stars tend to be very blue and very hot, and the very red stars, very cold stars, tend to be very dim. All of these stars along this so-called main sequence are stars that are in the prime of life. They're burning hydrogen. Burning hydrogen, I mean they're carrying out nuclear reactions that convert hydrogen to helium and produce photons that propagate outwards through the star and balance the gravitational pressure and prevent collapse. Now, there are some stars that don't fall in the main sequence. You have these things up here. You have very red, so very cold, but very bright stars. These are very big stars. These are called red giants. They're cold because they're red, but they're very bright because they're big. These are called red giants. And up here you even have some that are supergiants. They're very, very big and very bright and very cold. And these are things that once they run out of the fuel, the hydrogen fuel, they start burning the helium. So they start converting helium to even heavier elements, to elements like up to iron. Iron is pretty much where it stops, but all the other elements, all the other nucleosynthesis of all the other elements that are heavier than helium. And when that happens, they sort of grow, and these are the death throes. Okay, and these are up here, and then you have these things down here which are very hot because they're very blue, but they're very dim. Okay, these very, very, very dim, but very hot objects, very blue objects, are white dwarfs, which I'll talk a little bit about in a second. Okay, so for these guys, along all of these stars that are plotted here, these stars are all generating pressure by nuclear reactions of turning hydrogen to helium, and the energy basically propagates out as photons and balances the gravity. Okay, and that's the first mechanism. Okay, now, what are other mechanisms? Well, when the nuclear fuel is completely exhausted, there's nothing left for the star to burn or to convert into heavier elements. Then what happens is you have other mechanisms that are required to produce the outward pressure. And this is the leitmotif of this talk, is that the interactions between the microscopic constituents, I've said this several times already, are basically the source of the outward pressure. So we need to understand those interactions, right? So understanding these interactions is required to understand the stability of collapse against collapse of white dwarfs, neutron stars. And then for an object that is beyond a certain mass limit, none of these interactions that we know about can prevent collapse. And as far as we know, they collapse to nothing, to a black hole. Okay, so that's where we're going. This is the leitmotif. If this were a Wagner opera, everyone would be out the door right now. But this would be like, I don't know, this would be, the dense matter would be like Brunhilde, and this would be the theme that comes along with her, or something. I don't know, or Siegfried. Okay, so we want to model this stuff. Okay, what are you going to do? Well, a model is just that. It's not real necessarily or true, but it's useful. Okay, what is the most? This is the art of doing physics or anything or any kind of science, is figuring out what is important. Okay, and ignoring the stuff's not important within the regime that you're interested in studying stuff. So the most basic thing you can think of if you're going to model a matter is have a bunch of point particles that don't know about each other. These point particles don't interact in any way. Right? That's something called an ideal gas. It's ideal because it doesn't exist. It only exists in Plato's ideal realm, nowhere else. That and all the mathematics, right? But ideal gas, as we all know from high school science or from Chemistry 101 or Physics 161, they actually do exert a pressure. How do they do that if they don't know about each other? How do molecules that are point particles for our purposes whiz past each other, don't know they exist, can't bounce into each other, can't attract each other, can't repel each other? How do they produce a pressure? Where does that pressure come from? Well, it turns out it's a statistical thing. It comes from something called entropy, which you may or may not know about, but basically we know that, according to the second law of thermodynamics, that things tend towards disorder in the world. That's just an observation. Things tend to get more disordered generally. Okay, and as things get more disordered, what happens is if you're having a bunch of these particles occupying a small space, there's many, many more ways for them to occupy a large space than there's for them to occupy a small space. Therefore, what happens is, in order to increase disorder, there's more ways to be disordered here than there is here, so entropy tends to go this way, which means these particles tend to spread out. Now, they spread out without knowing about each other. So it's entirely a statistical effect, but something has to be pushing them out, right? So that's what we experience as pressure. But that's a statistical thing. It doesn't come from any kind of interaction between the point particles because they can interact with each other. It's just the fact that in this way they want to spread out because there's more ways for them to be spread out than there is for them to be all together, and therefore you exert a pressure. That's an ideal gas. Okay? This is what an ideal gas looks like. You probably are familiar with this. These are the pressure, the volume, and the temperature, right? And these are the isotherms. If you look at the pressure as a function of volume, for a given temperature, you'll notice that as you decrease volume, as you compress the stuff, the pressure increases. This is all a function of entropy, of statistics. But this does in fact happen, right? So the pressure increases as the volume gets smaller and as you compress. That's the most basic model for a classical gas. Okay? The next thing you want to do in your model is you want to put in interactions, right? Because this thing, ideal gas, okay, an ideal gas works for noble gases, right? Helium, neon, argon, xenon, krypton, what else is there? That's about it, right? I think. because they don't interact. They really do act, at least pretty closely, they're pretty closely approximated by an ideal gas. Or mixtures of gases also. So, you know, if you have very dilute gases or mixtures of gases, the ideal gas law seems to work pretty well, but it doesn't have everything. So if you want to improve your model and have other things that, you know, describe more details of your system, you need to put in not just these point particles, but you have to put in some interactions between your particles. Everyone with me? All right. So van der Waals, okay. Well, van der Waals has an equation of state that describes how particles might attract each other and repel each other. So there's interactions in there, there's energetic interactions in there that modifies the basic ideal gas type of model. And you know, we know that these interactions have to be essentially electromagnetic interactions, right? And we understand electromagnetism. We understand Maxwell's equations. But even though we understand electromagnetism, it's very, very, very difficult for a large number of particles to figure out, just starting from those basic principles, how things are going to interact. So we make simple models. We make a simple model where we have a repulsive component and we have an attractive component. And at long range, we say when they're far apart, they tend to attract each other. When they get too close, their hard cores sort of collide. And you know, we fit this to the data that we have, experiments, and we build a phenomenological model that maybe describes the systems we're dealing with some degree of accuracy. So if we had we do have a good understanding of electromagnetic interactions at a microscopic level, and from that we could in theory works, in practice it doesn't, right? But you could get the bulk properties, and if you had the bulk properties, you could get limits on the microscopic interactions, which is your model, which could be of various levels of sophistication. Now, the van der Waals, okay, basically you get, this is your attraction, which decreases your pressure. And this is your hard core. This is an excluded volume, which decreases your volume and which decreases the available volume that the things can move around in. And so what happens is if you put these things in and you fit those parameters A and B to the data, this is phenomenological, you get new behavior. If you're at a very high temperature, nothing much changes. This yellow line, it's still a yellow line. But as you go down in temperature, you find that something very strange happens. As you decrease the volume, you get to a certain point, and then if you decrease the volume, the pressure doesn't change. It follows this line. What's happening there? What happens as you go from here to here, and you're squeezing this stuff down, but the pressure doesn't change until you get to this point, and then all of a sudden it takes off, and you just change the pressure a little bit, and the thing goes crazy. Or change the volume a little bit, and the thing just goes crazy. Well, there's a phase transition happening here. You've encountered some new degrees of freedom that you've opened up. Okay? So this is a gas. This here is a liquid. This is not compressible. You try and squeeze it, it pushes back real hard. This doesn't. Between this point and this point, you're just changing the relative amount of gas and liquid that you have. You're having a phase transition that's happening here. This is stuff we all know probably, but you know, this is sort of the way where I'm going to be talking about the nuclear interactions, which I'm not going to get to because I'm going too slowly. But that's sort of the model. And of course, you know, this is the phase diagram that you're probably familiar with water, right? So this is water and this is water vapor, and this is where the transition happens as you go across. You go from water vapor to water, and if you're at a high enough temperature, then you don't really see a difference between water and water vapor, right? At this point, if you're below this point, this is the critical point right there. Above here, there's no real distinction between water and between gas and liquid. But once you get below the critical point, then there's a distinction, okay? So on this diagram, which is just sort of plotted differently essentially, you have this critical point where above this, there's a smooth transition between these two states. They're not really distinct states, whereas here there's a sudden transition. You're either a liquid or you're a gas, not both. You're a mixture, baby, but you're not both. Okay? This is sort of the way that I'm going to talk about nuclear interactions, following the same kind of thought pattern. So even though we understand electromagnetic interactions, we can model electromagnetic interactions with a potential, with a interaction that is very simple, like the van der Waals. Well, this is actually called the Leonard-Jones potential, but it's the same thing I showed you before. You have something that is repulsive at very short distances, has a very high power of the separation, and something that's that's fairly attractive at larger separations, this is the attraction, okay? And you fit those parameters and you get, you know, a van der Waals equation that sort of gives you a reasonably accurate description of, without fully understanding the details of the electromagnetic interaction, gives you a pretty good description of actually what matter does, which is sort of where I'm going with the nuclear force. The nuclear force is much more complex. Unlike this, which is central, right? The force or the interaction only depends on the separation. It doesn't depend on the relative orientation. The nuclear force is much more complex. It doesn't depend just on the separation of two nucleons, two protons, two neutrons, but it actually depends on their spins and how their spins are aligned or anti-aligned, or where they are relative to each other. It's much more complex. But the same kind of idea that I talked about here, we can sort of follow here. Okay? Build some kind of a model that's reasonable, that has things that are a paradigm that makes sense, okay? And then fit the details of it to experiments. Okay, that's what I'm talking about here. And I thought about leaving this blank because I don't, want to annoy people. But then again, I do it anyway, so I might as well. Okay, so I'll just show it to you, but don't pay attention to it. Okay? This is what it looks like. So it has actually 8. This is the one that I worked with. Okay, that's my advisor developed and his collaborators. But it has 18 terms. Each one of those terms is multiplied by a potential that looks something like this. But then there are various operators which represent, the relative spins. It's the tensor interaction, which is the orientation of the spins. There's a bunch of crap here that you don't really care about. The point is, it's the same process. Okay, that's the point that I want to make. That's all. So you don't have to think about that, and you can forget I showed you that. Okay, because Okay. So the interesting thing is, as work is done on the matter, as you compress it, new degrees of freedom become available to store energy, and you see new behavior. You see liquid-gas phase transition. Interesting. Okay. What kind of things might happen as you get denser? Okay. If you have, neutral atoms and you compress them eventually, you might, you put enough energy by doing work on them that you ionize them. At that point, your gas becomes a plasma. It's a different phase. It's different. It has different properties, because even though it's overall neutral, it's charged. The components are charged, and their charges are not necessarily screened. So it's different. That's you've introduced new modes that can hold energy. Okay. Now a white dwarf. Now we're getting to some interesting stuff. A white dwarf is actually neutral gas of charged particles, but the properties are determined by the kinetic energies of the electrons. Okay. And I'll talk more about that in a second. And eventually, if you keep sitting on the stuff and keep compressing it, your energies get high enough, you do enough work, enough energy goes into the system that you start producing nuclear reactions. This one in particular is called electron capture. So if you have ordinary matter with protons and electrons, and you compress it enough, eventually you start, the protons can capture the electrons, you can produce neutrons. So you get something that is mostly neutrons. And then you also have to create this little thing called a neutrino, because otherwise you can't conserve momentum, for those of you who care. But this thing flies off quickly, and you don't know it's there because you can't detect them really. You can, but they're very hard to detect. Okay? So basically what happens is you end up with a lot of neutrons and perhaps a small number of protons and electrons around, but a large number of neutrons held together gravitationally, like in a neutron star. At the most basic level, neutron star matter is basically a gas of neutrons, in the same way that a gas of water molecules is water vapor. Okay? But there are some different properties. And then at higher energies, you can have even more particles, different modes that can be formed. If you get above 300 mega electron volts, which is a unit of energy, then you can produce something called pi mesons, according to this good old equation, where this is the mass of a meson, pi meson, and you can produce even more. There's even more places for energy to go. There's all kinds of new phases that happen. Okay, all kinds of new behavior that happens. And I'm not going to go into detail because this is a very rich field of study. But here's a corresponding phase diagram. So this was a phase diagram for water up here. Here's a phase diagram. Admittedly, it is not. It's somewhat hypothetical. It's based. There's some data that goes into it. There's some data that go into it. Data is plural, as I always tell my students. But a lot of it's based on theory, and we surmise this is something. There's something like this. So if you're at very, very, very high density, but low temperature, you have something perhaps called a quark gas. If you're at very high temperatures, you'll have something that is equivalent of a plasma, a charged thing, which is made of quarks and antiquarks and gluons, perhaps. Now, when I show this, perhaps you might ask me, well, yeah, you're telling me about this. Where does this stuff exist? Do you ever see this stuff? Are you just making this up? Well, actually, there's 3 places that you actually do have it. Okay? The first place is everywhere, but not now. Back in the early universe, like just fractions of a second before the Big Bang, the entire universe was basically a plasma of quarks and gluons and antiquarks, because things hadn't cooled down enough to actually settle into nucleons, then into atoms and blah, 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 and all that stuff. Okay? 2 other places that you actually can find this stuff, I think. One of them, surprisingly enough, is Long Island. Anyone know why Long Island, New York? Something called Brookhaven National Laboratory. Something called the relativistic heavy ion collider. And they smash gold atoms, gold nuclei together at very high energies and believe that they have signatures of something like this forming for a short period of time. The other place, Geneva, okay, at CERN. So those are three places I know that it probably does exist. But, you know, maybe there's other places too that we don't know about. Anyway, okay. In here you have a critical point here. You have sort of the equivalent of a gas-liquid transition that you had up here, right? You have here a superfluid, a fluid that moves without any resistance. But it's a superfluid not of atoms, but a superfluid of neutrons and protons that moves with no resistance. This is actually about the density regime of a real nucleus. Many nuclei, depending on the number of protons and neutrons in the nucleus, are actually superfluids. Maybe you knew that, maybe you didn't, okay? So this right here is about the density of a nucleus, right there, okay? In here you have a transition, like we did up here. No, the other picture, we had transition from basically what's a gas to what's essentially liquid. And if it's a cold enough liquid, it's a superfluid liquid of neutrons and protons instead of just a regular liquid of neutrons and protons. Here you have pions that happen, all kinds of things going on, all kinds of interesting things going on. Here you have something that basically is like a semiconductor, but a semiconductor that is not based on germanium or silicon, but a superconductor based on neutrons, protons, and alpha particles. Basically, a transition happens here from an insulator to a conductor, where where you can actually have current be, in principle, transferred through the material. It's called the Mott transition. You may or may not be familiar with it. Anyway, this is the kind of thing we're talking about. Now, I put a lot of stuff up here, but this is what's interesting. This is the richness of the field, which depends so much on the details of what the interactions look like. And I have to hurry up. So, very quickly, we had the base model for classical stuff. Well, if you're dealing with quantum stuff, you need an equivalent of an ideal gas for a quantum system. And for a quantum system, okay, you basically, so this thing here, this is the distribution. This basically tells you what the probability is of having in a classical gas, a probability of having a particular energy. It depends on the temperature. And from this, you can actually derive the relationship PV equals nRT. Okay? And the pressure is due to entropy, the classical statistics, the Maxwell-Boltzmann statistics. Don't worry about the details of that. I'm just saying it. When you're dealing with an ideal quantum gas, so quantum particles, as opposed to classical particles that do not interact, you have an equivalent of, and they have spin 1/2. This is very important. There's two kinds of particles in the world. Particles that have half-integer spin and particles that have integer spin. Most of the matter we deal with is stuff that has half-integer spin. Electrons are half-integers. Protons, neutrons, half-integers. Some atoms are like liquid helium forms, superfluid liquid helium forms, because those are actually combined into something that looks like it has unit spin. But anyway, if they have half-integer spin, they obey a different kind of distribution called the Fermi-Dirac distribution, which instead of this business looks something like this. This corresponds to classical particles, which are identical but distinguishable. Quantum particles are identical but indistinguishable. What does that mean? I'll let you think about it. You can't, if I have two basketballs that look the same, I still know this basketball is different from this basketball. If I have two electrons, they look the same and I can't tell them apart. If I switch them, I don't know I've switched them. There's no way to tell, because that's just a property of, I'd have to talk a lot more about it, but that's what this basically tells you. And here you have a pressure, once again, not due to interactions, but due to quantum statistics. And that's all I'm going to say about that. But what I will say, okay, is this is how this works. Okay, if you imagine that you were on a plane, okay, you always fill in the plane from the back to the front, right? So since these are quantum particles, like electrons, for example, there are only discrete levels that those particles can occupy. If you're a classical particle, you can be anywhere at any energy level in here, right? But if you're a quantum particle, then there are discrete levels, like your hydrogen atom levels or something, where the only things that can be occupied. So if you're on a plane, okay, basically every seat is like a quantum level, right? And as you go up, as you fill in the plane, the higher energy levels correspond to the front of the plane, right? Now, Fermi-Dirac statistics, spin 1/2 particles, have to obey the principle that you can never have two passengers in one seat. Okay? The other kind of quantum particle bosons, you can have as many people as you want in one seat and they don't care, they're very friendly. But these guys don't like each other so much, like electrons in the hydrogen atom, right? fill up a hydrogen atom. As you put more electrons in, they go into higher and higher energy states. Same thing, as you send in passengers, those passengers go to the bottom, to the back of the plane, and you fill in. And as you fill more stuff in, the new passengers that come in have higher energy because they're sitting higher up because they can't sit back down here. This is at zero temperature when they're not moving around very much. If the temperature is higher, then they have energy, they can move around, so you can have holes, spaces, seats where no one's sitting in, and this is at higher temperature. So what happens is they pile up. And this leads to a different kind of statistics and a different relationship for pressure. That's all I want to really say here. Just very briefly, once again, don't really pay attention to this, but this is the distribution for classical particles. So this is the average speed of a classical particle for a given temperature, and as the temperature increases, the average speed increases. This is the occupancy of a quantum gas. For very low temperatures, like this black line, everything below a certain energy, that level, that last aisle that was filled, okay, is full. Everything below it is empty. As people get out of their seats, you have some spilling over and stuff comes out. These are different statistics and lead to a different kind of a pressure, different kind of relationship for pressure. That's all I wanted to say there. Moving on, even further, so if you put even more energy into a system by sitting on it even more, in principle, you can start to excite internal states of a nucleon, of a neutron, for example. At which point, a neutron is made up of two so-called up quarks and a down quark exchanging gluons. If each one of these things is a nucleus, like a neutron, there's all kinds of stuff going on inside the neutron, but it's entirely enclosed. As you increase the pressure a great deal and you increase the density, what happens is you get one very big nucleon, essentially, because now these constituents are free to move around. You get a plasma. You get all these internal degrees of freedom that can move around within this huge thing, this huge neutron, essentially, or something, very big super neutron. This is, it's what I would call a quark gas, or quark gluon plasma, actually. Okay, moving along very quickly to finish up. I started the talk with an episode from the beginning of my career in higher education as a student. So the last thing I'm going to show is I'm going to show a calculation I did towards the end of my career as a student when I was a PhD student, where we did a calculation based on the things I've told you of what the energy would be of a gas of a neutron, of neutrons, of a bunch of neutrons together as a function of density. So at very, very short distances, short densities, not short distances, short densities, okay, this is a Fermi, which is 10 to the minus 15th meters, you basically are dominated by the Fermi gas, the pressure of those fermions. And the interactions actually are attractive at long distances, so actually the energy is decreased because of the interactions, short-range interactions between the nuclei. As you get more dense, you find that the short-range interactions become repulsive. And so what would normally just give you this much energy gives you a lot more energy if you try and squeeze it. So that big ugly thing I showed you gives you an energy that is much larger because you produce a lot more pressure based on the details of the calculation. I just wanted to show it to you just to illustrate, okay? And one thing that's useful is you can make a prediction. You can make a prediction. We made some predictions with this calculation about what the maximum mass of a neutron star could be. So if you look at as a function of the core density of a neutron star, we did some calculations of how massive a star can be before it collapses to beyond a neutron star. And we found that, for our best potential, our best interaction, we could get stars that were about 2.2 solar masses. Anything beyond that would collapse, as far as we're concerned, would collapse to a black hole. If we allow there to be quark matter inside the neutron stars, then that goes down a little bit. But that's speculative. So that's a prediction. And then people can go out and see if they can find neutron stars that are heavier than that. If they do, then there's something wrong with our theory. But anyway, this is from the end of my stuff. So how dense can you get? Last slide. Well, can you get denser than an atom? Yes. A white dwarf is basically a large atom. It's a huge gravitationally bound atom, right? It's a whole bunch of protons and neutrons. And then you have these electrons whizzing around the outside, which provide the pressure. They're like a big atom. An atom which is about less than 1.4 solar masses, but about the size of the Earth. Well, can you get as dense as a nucleus? Well, a neutron star is supported by nuclear interactions, and that can be a mass as large as 2.2 solar masses, but about the size of a city. I'm sorry, not a city. Did I make a mistake? Yeah, city, that's right. So this is the size of the Earth, this is the size of a city, right? So this is like a big nucleus. A neutron star is something like a big nucleus that's bound gravitationally. And if you have denser stuff than a nucleon, you could have stuff that is like a big, rather than a big nucleus, a big nucleon, a big neutron. A quark gluon plasma would like to be a huge neutron or a huge proton or something, right? Very speculative. And then anything more than that, then black holes, who knows, to be determined. This is still an area of active research. So that is pretty much everything that I have to tell you. And hopefully that wasn't too boring. Yeah.